Welcome to Episode 4 in Topics in ECE. In Episode 3, we learned how to analyze circuits using Kirchhoff's voltage and current laws and ultimately a voltage divider circuit. As an example of a circuit that's really ubiquitous in all of electronic design, at least for analog circuits, which is what we're going to be discussing today. Today, we'll review a little bit of Episode 3 in case you didn't see that one yet. But we'll also look at some more powerful theorems like linearity and Thevenin equivalent circuits. But our main goal today is to be able to look at a schematic and figure out what's going on. And we're going to do that by learning to translate circuit diagrams such as this into functional block diagrams that provide the information on how the signal's changed as it flows through the circuit. And I'm going to refer to that as parsing schematics into block diagrams. And here I'm borrowing that term parsing from computing, where it generally means analyze into parts and describe their syntactic roles. So today we're going to learn how to take a schematic such as this one and walk through it and understand what each portion of it does, and come up with a block diagram. So here's our topic list. We'll start with that review of Episode 3. Then we'll cover the new circuit level theory, linearity and Thevenin equivalence, but we're going to apply that to voltage amplifiers, such as this one that we met in the previous episode, and how we can take something this complicated or even more complicated, such as in the actual circuit, with these extra components around it, and observe it in a more simple way. And we'll define and discuss the absolutely critically important parameters that characterize an amplifier, which include its input resistance, or in general input impedance, its output resistance, and its gain. And we'll learn that when we embed that amplifier into a larger circuit, we need to be concerned with none other than voltage division. Here we've got a source resistance from the circuits that precede the amplifier, and here we have the input resistance of the amplifier, and look, there's a voltage divider. So we'll look at the loaded voltage gain as well as the unloaded voltage gain. And that will then prepare us for parsing the schematics into the block diagrams. So let's get started. The first thing we need to learn how to do all of this is some schematics to analyze. And the one we're going to be looking at today came from this website. It's a guitar amplifier with 2 inputs on 1/4-inch jacks. And it's very similar to some of the circuits that we looked at in Episode 3, such as this. But there's a lot more circuits here today. So today's goal is to understand this particular schematic and how the input signals are processed as they flow through. And through, and through, and ultimately to the speaker. Now, I want to emphasize this is not a video about guitar amplifiers. I'm just using this as a typical example of a circuit schematic. Our real goal is to understand how we analyze these circuits, because the analysis techniques are general, and they will allow us to attack many other circuits in the future. Now, before we dive in, one last set of important notes. This is from page 1 of our example schematic. We will talk about tube amplifiers a little bit, and those, as you probably know, run on very high voltages, and you have to be very careful because they can be hazardous. Even the power supply section of the amplifier will contain circuitry that's connected to the mains, which could be 120 volts or 240 volts. So don't mess around with this stuff until you know what you're doing, at least not physically. The other notes here pertain to reading the schematic values on components. The resistor values are given in ohms, so that's simple, and the capacitor values are in microfarads. So C5 here is labeled 0.1, that's 0.1 microfarads or 100 nanofarads. This is 0.001 microfarads or 1 nanofarad. Except in the case of this one where it's 100p, which means it's 100 picofarads. Note 3 here I'm not really concerned about in today's episode, but note 4 is important. they show circuit grounds with this symbol. And that's often used as a chassis ground, which they use this symbol for. So these are often reversed. I will also use this symbol for ground, and it's the same ground as the one next to it here. So anytime you see either of these two symbols, that means it's connected to ground. So let's dive in, starting with that review from episode 3. In episode 3, we looked at a small piece of the schematic for a Fender Champion 30 guitar amp. And we considered the case where the guitar is plugged into jack 2 only. And when that happens, this signal goes through this resistor and then through this resistor to ground. And we learned that that creates voltage division. The signal at this point here is only 1/2 the signal level of the input. And that's because we recognized these two resistors in series, one to ground, one to the signal, and a tap point in between, as this circuit, which we call the voltage divider. Everybody calls the voltage divider. It's really, really common. And using Kirchhoff's voltage law and current law, we came up with this expression for the tap point voltage V1, given a voltage coming into it of VB in this case. So V1 is VB multiplied by R1 over the sum of the two resistors. R1 is the lower resistor. So for example, if R1 is 1 k ohms and R2 is 9 k ohms, then the total is 10. So you have 1k over 10k, which is the number 0.1. So that means the output is 0.1 times the input. Or in the case of our example circuit with 33 k ohm resistors in each place, this fraction would of course be 0.5. And the signal here is only 1/2 of the input signal amplitude, as you see in the graphs. Now that's all nice and simple if there's nothing connected to this node V1. But in our example circuit, that point feeds into the rest of the circuitry. So we've got to worry about what other resistances to ground would be on this node. Now for the audio signals coming in from this jack, the two capacitors here, C1 and C2, just couple the signal through, so we don't consider them. Just a connection from this point here to this point here, and we see that R4 is to ground on this node. So it's in parallel to ground with R1. So that's the case on the right-hand side. So R1 and R2 are 33 k ohms, and RL, let's say, is 510 k ohms. And we could analyze this circuit with Kirchhoff's voltage law and Kirchhoff's current law and nodal analysis and all that great stuff, except it's much better to just rely on what we already know. We already know how a voltage divider works, and so we just look at these two resistors, they're in parallel, so let's come up with an equivalent parallel value. And that's given by the formula 1 over the quantity 1 over R1 plus 1 over RL. So we conceptually look at these as a single resistor, and then we're back to our basic voltage divider that only has two resistors, except this one's now REQ. And we can write directly what the output voltage is. But it's even better than that. Let's assume that RL is much bigger than R1. Remember, this is 33K, this is 510K in this example. So this is really big compared to that. So it doesn't really change the value of R1 very much. So the equivalent value of these two in parallel is, as it says over here, very nearly just R1. So after we figured that out in episode 3, we labeled this first section of the circuitry the signal summing circuit. And we drew a vertical line here because this circuit is really separated from the next one, which we also covered. It's an amplifier. We'll review that later in this episode. But the important thing conceptually is that we can draw this line here, and we can do that because this second circuit did not load the first circuit significantly. So this summing circuit works the same whether we connect this next one up or not. And that's really important in design and understanding of circuits. As we'll see today, the amplifier here in the middle has what's called an output impedance, which is close to 0 ohms, so it can drive into this next circuitry and not be affected by its connection to it. This next circuitry here after the amplifier section will not load the amplifier significantly. So instead of trying to solve this complicated looking circuit with Kirchhoff's laws and nodal analysis and whatnot, we've broken it down into simpler pieces, and that's how engineering is done. Things are broken into subsections, or sometimes called subsystems. But before we can continue parsing our schematic into the block diagram, we need to do a little bit more circuit theory background. In particular, let's look at the topic called linearity and Thevenin equivalent circuits. Now, this is circuit theory, so this slide is a little bit busy, and there's an awful lot that can be said about these two topics. But here's the essential bits. Remember, our amplifier has two inputs labeled jacks 1 and 2 here, and they're shown in the diagram over on the right. How can we say that these two resistors actually sum those two signals together? Well, that's the basic concept of linearity. For what are called linear circuits, the output, the total output, can be found by, number one, finding the output from each individual source, with the other source values set to 0. So in our example circuit, we have two signals coming in. Now think of each one of these as a voltage source to ground, because what gets plugged in here is the guitar, and the guitar has a pickup, and that pickup outputs a voltage. And if there's two guitars plugged in, as shown here, then the two signals from the two guitars' pickups are going to sum together. And that result comes directly from this statement. We find the output from each of the individual sources. Each one is going to look like a voltage divided version of the input. Then, for linear circuits, we can find the total output simply by adding the individual outputs together. And that's what you see on the right-hand side. Vs, that's the voltage at this node, is 1/2 of Vn1 plus 1/2 of Vn2. Now, what is going on here? Why is there an Rs? Well, that has to do with what's called Thevenin's theorem. So let's go back to the previous slide and take a look at Thevenin's theorem. What Thevenin's theorem says is that all the stuff circled in yellow can be replaced by a single voltage source in series with a resistor. Now, in this particular example, that doesn't sound too earth-shattering because there's only a couple of resistors here and a couple of input sources. But we've got 4 components that now are being replaced with only 2. But this works for much more complicated circuits too. Thevenin's theorem says we can replace a complex linear circuit, any linear circuit, with one of these voltage sources in series with a source impedance or resistance. Now, if you've taken courses in school or if you've read about Thevenin's theorem, you know that some practice is needed to figure out what the source resistance is. And I'm just going to refer you to the Wikipedia page and zoom in briefly on this slide here that talks about it, and you can read that. But I'll summarize that procedure as follows. To find out the source resistance, Rs here, we stand at the output node and we look back into the circuit that we're going to replace with this simpler one. And we set all the voltages to 0. So this point here is ground, and this point here is ground. So if we stand here, we see R1 to ground and R2 to ground, and they're in parallel. 22K each, and so Rs is 11K. If you want to know more, you want to look into this in more depth, then again, I would encourage you to go to the Wikipedia page on Thevenin's theorem and read about it. And this is an incredibly powerful thing to know. It is, in fact, the basis of the characterization of voltage amplifiers in terms of what we call an input resistance, the internal voltage gain, and an output resistance. So that's our next topic. Now, voltage amplifiers and amplifiers in general come in a very wide range of types. Indeed, the guitar amp is itself an amplifier that takes a signal from the guitar that's maybe 100 millivolts and sends about 35 volts peak to peak to the speakers or more. And that whole amplifier can be characterized using Thevenin equivalent circuits in terms of an input resistance, a voltage gain, and an output resistance. But right now we're going to focus on a somewhat simpler goal, which is understanding what this piece of the circuitry does. And it's built around an operational amplifier. And the part number in this case is RC4558, which is actually a dual version of the classic LM741 operational amplifier. And what exactly is an op-amp? Well, we talked briefly about it in episode 3. And we essentially looked at this circuitry, which has the op-amp here, and then a couple of feedback resistors, R2 and R1. And in that episode, we derived an expression for the overall gain from the input, which is here, V input, to the output. And we'll see that in a minute. But before we leave this slide, let's look at the right-hand side, which is the internal diagram for this op-amp. And this is the first and last time we're going to look at this, because in general you don't need to know all the details of what's inside. We're using Thevenin's theorem to simplify things. All we want to know is the voltage gain from this input to the output, plus a couple of other things like the input resistance and the output resistance. So here's the amplifier voltage gain stage in our circuit. And down below it is a very simplified view of what we're trying to do. We have abstracted out the details of this and replaced it with a Thevenin source. And now we have an amplifier that we're going to examine. And that drives into the rest of the circuitry, which is in yellow here. And I've represented that just as a load resistance to ground from this output node labeled Vout. Of course, if all goes well, then this thing will take some input signal, such as on the left, and produce a larger version of it over here on the right. And the ratio of amplitude of the output to the input is, of course, the voltage gain. So how do we find out what that voltage gain is? Well, we have to examine this circuit. And at first glance, it looks a little complicated because there are a lot of components here. But we can simplify it a lot if we examine it at what we call midband, which in this case I'm going to take as audio frequencies from about, say, 100 hertz up to 10 kilohertz, or whatever the guitar puts out. And when we focus in on just those frequencies, we can do things like look at C2, which is 100 picofarads, and realize that the reactance of that, we're going to examine this in detail coming up, but the reactance of this is very large compared to the 270K and especially the 11K source resistance that's driving into it. So this capacitor acts like it's not even there for the audio signals that we care about. And likewise for C4 and for C3, it acts like a direct connection to ground because it's very big. It's 2.2 microfarads. So we just have this resistor R4, this resistor R5, and R3 over here at the input, in addition to everything that's inside this amp. Oh, wait, we can simplify that. That's what we're trying to do here. What we need to know about what's going on here is that the input drives into this plus terminal. And the designers have configured the circuitry so that that looks almost like an open circuit, like it's not even connected, except the signal does go in here, present itself, and through this configuration, as we talked about in episode 3, it's multiplied by a gain 1 plus R2 over R1. The other nice thing about the internals of this is that the output resistance from this operational amplifier is very, very low. So it can drive into just about anything. And we'll see what that means in a minute. So we can take everything we've just said and use it together with Thevenin's theorem and come up with a replacement for all the circuitry, including what's inside here, with just 3 components. Let's look at the output of this first. This is what's called a controlled voltage source. The value of it depends on what the input is. So it's a number times Vn. And that number is, as I just said, 1 plus, well, nope, it's not called R2 and R1 anymore, but it's R4 and R5 taking the place of those. So here's the formula. If you plug in these values, 7.5K and 1.5K, works out to be a voltage gain of 6. Now, as we said, the nice thing about these op-amps is that driving into the plus terminal looks like pretty much an open circuit. It doesn't load anything. However, there is an explicit resistor here, R3 to ground, which will load our source circuitry somewhat, but not much because it's 270K. So where does Thevenin's theorem come in? Well, Thevenin's theorem allows us to represent what's going on at the output of this device with this controlled voltage source in series with a resistance. And that will allow us to figure out what goes on when we load the output of the circuitry with the following circuits. Similarly, on the input side, Ri loads the source, as we said. And so here's what we have. We have a Thevenin equivalent circuit to represent the input signals. Driving into this Ri, which we said is 270 k ohms, thereabouts, we have a voltage gain provided by the amplifier of 6. Some people call that 6 volts per volt, but it's unitless, so I'm just calling it 6. And then we have an output resistance, which is approximately 0. And that output node is connected to, well, I'm calling it R load here, 1.5K. Where does that come from? Well, it's an approximation for everything to the right of the output node. If this is a coupling capacitor, then you can see 1.5K to ground here. It's a little bit more complicated than that. At low frequencies, the net resistance is somewhat higher, but as we're going to see, that doesn't really matter. And it doesn't matter because the output resistance of the Opamp circuit is close to 0 ohms. Now, there's something called loaded voltage gain. This is really important, so let's spend a couple of minutes on this. Remember, Vs models the guitar input voltage sources, and Vout is the hopefully amplified voltage that's driving into the next stage. We've already said that the voltage gain of the Opamp circuitry is 6. However, there is a small problem with loading. And what does that mean? It means you've got voltage dividers here. There's one that's composed of RS and RI, and another one that's composed of RO and RL. Let's take them one at a time. On the left-hand side, we've got a source resistance of 11K, and it's driving into RI, which is, what's that, 270K. So the source voltage gets divided down a little bit. It's a little bit smaller than it would be if it was driving into a pure open circuit. And we know the formula for voltage dividers because we learned it. It's super important. It's Ri over Ri plus Rs in this case. And if you crunch the numbers, that comes out over here on the right as 0.96. So about 96% of the source voltage actually makes it into the amplifier. Then this signal Vi on this node is multiplied by 6, which is AV0. And at the output, we have another voltage divider. Fortunately, it's not much at all because we said this Rout is close to 0. So the expression is RL over RL plus Rout. And if Rout is 0, then you have RL over RL. And that's just 1. So that's the third term here. So the overall result is 0.96 times 6 times 1. That's 5.77, and it's approximately 6. To two significant digits is 5.8, but we don't really care. It's basically 6. The output is 6 times bigger than the source. As an example, if we strum the guitar pretty hard, we may have as much as a volt here, and that would become 5.77 volts, about 6 volts, on the output here driving into the next stage. Okay, we've covered a lot actually, and we've completed the background in circuit theory that we need to begin our main task, which is parsing the schematic into a block diagram so that we can understand what's going on. We started with this goal, pulling this schematic from the web and trying to understand what happens to signals as they flow through it. And to do that, we're going to have to recognize some common analog subcircuits. And that's going to take some time. So I think I'm going to leave this here as the end of part 1. We'll have a second part to this video. But here's a preview of what we're going to do in that second video. We're going to use what we've learned to take the circuits that we've already understood, which is this input here and this amplifier, and we're going to build on that. For example, we skipped D1 and D2. What are those? Well, I claim they're an amplitude protection limiter circuit, so we'll talk about that. We kind of skipped over C1 and C2. We kind of ignored them at midband, but why are they there? Well, we'll talk about that. And then we'll even get into some of the interesting things about guitar amps, which is that guitarists sometimes like distortion. They actually don't want clean signals all the time. And we'll see in the next video that this is a distortion generating circuit, or can be, depending on how it's configured. And over here on the right is another one, but this one's made out of vacuum tubes. So some pretty cool stuff coming up. But for now, I'll say thanks for watching, and I hope you've learned some things in this particular video. And we will definitely use those things in future videos to try to understand this whole circuitry, which is going to take probably more than one video. Anyway, thanks for watching.